couldn't turn the AC down so low on the campus.
But the clock doesn't work.
No, it doesn't work in subvariety.
Good to know. That's been nice.
You know? After he told me the reason we were there.
So the up and down works here.
Yeah.
Okay.
For
I just turned it off.
And it is late.
That's fine. Yeah.
I think Dr. Miller, I want
Yeah.
to do something first. He's gonna introduce you.
Oh
And
yeah,
then-
yeah. He's going to.
Yeah, and then I'm going to switch to your slides.
Yeah, and then I can just press this
To go,
down. Right?
yeah, this is to go next and up is to go
Yeah. Okay.
E4.
Yeah.
Yeah. This is the next slide to go back and the laser.
Thank you. Thank you. So if I speak people here, but sorry, if I speak people here.
Yes.
Okay, so I think it's time to start the event. So this is the inaugural event for the IMSA monthly lecture series to start. The topic of this series is geometry of the quotation bundle and hyperbolicity. Hyperbolicity will play an important role in this series, but there are other questions that we are also interested in. And we're interested in properties, geometric properties of projective varieties for which the quotation bundle has some positivity properties. So apart from the various forms of hyperbolicity questions, we are interested, for example, in a topic that is of interest to me, which, for example, is how different degrees of abundance of symmetric differentials on a projective variety, which is a measurement of positivity of the Gaussian bundle, is reflected on the topology. So there's many different aspects that we'll touch in this series. And you can, if you go to our website, we have some open problems and conjectures on the, that we'll be interested in, and we'll be adding them as the lecture series goes on. The organizing committee of this lecture series is Damon Brodsbeck from the University of Lorraine, myself, Natalia Garcia Fritz from Pontificia Universidade Católica de Chile, Stephen Liu at the University of Quebec à Montreal, and Jorge Vitório Pereira at IMPA in Brazil. The talks are always going to be in-person talks, at least that's the aim, that will be zoomed for a broader audience. The time of the talks is going to be always around this time so that they can reach the Americas and Europe well. The talks themselves will have always a component for the broader audience in algebraic geometry and complex geometry, and they'll have a component of say 60%, 50% for the more specialists. But graduate students with interest or young researchers are very welcome to this lecture series to learn about the topic. The lectures are going to happen in several places. Some of them will happen here at IMSA, University of Miami, but there will be talks at all the universities that of the organizers. All right, so that's I think the next talk will be at the University of Lorraine, and it will be on December 13th. So the talks will be on Fridays. This is an exception. Due to several holidays in different countries, force us to do this talk on a Wednesday. The talks of today are going to be first talk of Professor Yum-Tong Siu from Harvard University. I'm very happy that you're here. His title is Hyperbolicity and holomorphic jet differentials. He's been a moving force, a guiding force of this topic. By the way, I'd like to honor Professor Demey, another very important researcher that recently passed away, unfortunately. And then the second talk is by Professor Izet Kuskun about algebraic hyperbolicity of hypersurfaces and length type conjectures. So these are interesting talks. They are both about hyperbolicity, but they come from different directions. So hopefully that will be a broad approach to this type of questions. So I think now I'd like to introduce or to bring Professor Yum-Tong Siu to start the first talk.
Well, thank you very much, all the organizers, the work they have done to start this series. And it's my great honor to be here, seeing many old friends as well. And the talk is on hyperbolicity and holomorphic jet differentials. And we'll discuss hyperbolicity in function theory. In particular, the question to reduce the lower bound for the degree of a generic n-dimensional hypersurface to be hyperbolic. From the best known bound to this point, given there, which is n log n to the power n to polynomial order n, that means we are able to reduce it to n to a certain power. The technique used is to combine the techniques from the abelian variety setting and the complex projective space setting. For good list of references up to the best known result, I put it here. It is a particular paper, and it has a long list of references and also about the history and so forth. So it's a good place to look up for references. And we'll also discuss the analogy between hyperbolicity in function theory and in number theory. For abelian varieties, differentiation in jet differentials in function theory is replaced by the difference map in number theory. In the case of results on rational points in subvariety over a number of k in an abelian variety. And the hope is that similar implementation for hypersurface setting can be done. But at this point, it is not clear how to proceed. I have some ideas, but they are not mature enough to be presented at this point. Now, there are different notions of hyperbolicity. So in function theory, there are several notions attributed to various people. For example, Kobayashi hyperbolicity, Brody hyperbolicity, and so forth. And to save time, I don't want to go into the details of various hyperbolicity. So for convenience, we'll use hyperbolicity only to mean the following in function theory. A compact complex manifold X is hyperbolic if there exists no non-constant holomorphic map from the complex affine line to X. So it's also known as an entire curve. A slightly weaker version is the following. A compact complex manifold X is almost hyperbolic. This is not a standard term, just for the talk here. If there exists a proper subvariety inside X, which we call Y, such that the image of any non-constant holomorphic map from C is contained in Y. A natural condition for X to be almost hyperbolic is the ampleness of the canonical line bundle. This was conjectured by Phil Griffiths, Serge Lang, and others. And personally, actually, I'm very much indebted to Phil Griffiths and Serge Lang for getting me interested in the topic itself. While I was at Yale in the 70s. In the setting of number theory, when X is defined over a number field F, with the canonical line bundle ample, the conjecture is that the set of all k rational F, so this is a typo, this is F rational points of X, is contained in a proper subvariety of X. The analogy between function theory and number theory was suggested by Lang. Paul Voiter in the early 1980s came up with a formal parallelism between the linear theory and Diophantine approximation. Though the number theory situation is much deeper and far more complicated than the function theory situation, appropriate modifications of some techniques developed for function theory are applicable to the number theory setting. Most progress has been made in two areas. One is complex submanifolds of abelian varieties. Another is complex hypersurface degree delta in the projective space of dimension n+1 with delta sufficiently large relative to n. The best lower bound delta is conjectured to be 2n+2, is linear in n. There are also analogous problems concerning entire curves on complements of submanifolds in abelian varieties and complex hypersurfaces. They can be handled similarly, which we will not discuss. For the setting of a complex submanifold in abelian variety, the most important paper is Bloch's theorem in 1926, which states that the Zariski closure of an entire curve in an abelian variety is the translate of an abelian subvariety. It means that a complex submanifold X of an abelian variety which does not contain the translate of an invariant subvariety is hyperbolic. And if the canonical line is ample, X cannot be the translate of abelian variety because in that case it will be completely flat, and therefore must be almost hyperbolic. Okay, so that is the work of Bloch. So I explain here Bloch's techniques in more detail. In the first place, they were used in number theory. In the second place, the best way to handle the complex hypersurface case is to modify Bloch's techniques in a abelian setting. So I want to explain a bit about that situation. So in his 1926 paper on entire curves in a abelian variety of dimension 3, Bloch introduced important techniques to investigate hyperbolicity. The language and style of Bloch's paper are very different from papers published in today's mathematical journals. The description of his argument is very concise. He considered only the case of abelian variety of dimension 3, but the same arguments can be made precise and applicable to any general dimension, some generalizable to arbitrary complex manifolds. An interpretation of Bloch's language into modern setting I gave in an exposition in the volume for Abel's 200th birthday year. So you'd be interested if you look at it. In the abelian variety setting, Bloch introduced holomorphic jet differentials vanishing on an ample divisor. And that turns out to be a really important thing. To make their pullbacks on the entire curves vanish. He considered holomorphic jet differentials by using the position forgetting map from the space of jets, and by using the field extension of meromorphic functions from a holomorphic map between complex manifold with generically finite fiber. So there are two things here. First, he introduced holomorphic jet differentials and tell people how to use it, namely to make their pullbacks vanish. Second, how to actually get them by using this technique. Okay. So let me explain what a holomorphic jet differential means. So a holomorphic jet differential, omega, the order k and weight m on a complex manifold X with local coordinates z1, zn is locally a polynomial in the differentials. So the differential order is from 1 to k of homogeneous weight and m, and then the coefficients are holomorphic in the local coordinates, and the weight is computed by assigning weight nu to the nth order differential. The vanishing of omega local subvariety D means that all the coefficients vanish. That's what is meant. And if you have an open neighborhood of 0 in C and a holomorphic map from it to X, the condition of the vanishing of the pullback means the vanishing of the coefficient d zeta raised to the power m for all local parameterization. Okay. Because when you pull back, it becomes a holomorphic jet differential on C. And then everything is expressed in terms of zeta. And the coefficient of d zeta to m is only one part of that. Okay. There's no need to consider the coefficients of other monomials of the higher order differentials, because when you pull back, you get a differential order of weight m, so there are others present. The reason why there's no need to consider is, for example, if you look at the case Fw times d squared W, that is the part for the second differential, second order differential. If you have the change of parameters, you see that you end up with this. So the vanishing of this is a consequence of vanishing of this, of course, with all choices of parameters. So if you use the vanishing for all choices of parameters, it doesn't matter whether you look at the higher order differentials or not. all you need to do is the first order differential raised to that power equal to the weight. Okay. So the important thing is about this vanishing, because that's the tool for handling everything, for handling the entire curve. So it's now usually called a Schwarz lemma. Why is it called Schwarz lemma? Because the Schwarz lemma deals with a holomorphic function with certain bound. Okay, and then when the target is like hyperbolic, it's more or less like behave more like a bounded domain situation. So that's why there's the name Schwarz lemma. So Schwarz lemma for entire curves. So when X is a compact complex manifold complex dimension n, and omega is a holomorphic jet differential order k and weight m, vanishing on an ample divisor. It's important that it's ample, it doesn't matter what it is. And then you let f be a map from C to X, defining the entire curve. The pullback, then must be identically zero. So that is the important statement. That as long as you have a holomorphic jet differential vanished on an M-pole, then the pullback is identically zero. That is the Schwarz lemma. And of course, the target itself is not bounded or anything, but the target itself emits holomorphic jet differential, and the Schwarz lemma is sort of a generalization of the usual Schwarz lemma. And let me explain a bit how it's proved, because this is important. The important part is the use of never-linear theory, namely the logarithmic derivative lemma. So it's proved by contradiction. Assume that the pullback is not identically zero. And here is the main technique, which actually was introduced by Bloch. How do you prove it's vanishing? So Bloch's idea was to look at a finite number of global meromorphic functions on X. Okay, that's very strange. You suddenly look at global meromorphic functions on X with the following properties. First, for every point on X, there exists some nu such that some branches of the log of these meromorphic functions form a local coordinate system. Right? So of course, the choice depends on the point P. But the strange thing is that instead of usual local coordinate system, you use a global meromorphic function and take the log as a local coordinate system. Okay, that is a very ingenious step. And the conclusion is that once you do that, then your omega can be expressed in terms of these local coordinate systems. Okay. And in terms of these local coordinate systems, the coefficient is bounded. That's the only point. So when you pull back, you get a constant, and then pull back on the differentials of the log of these global meromorphic functions. Okay. And they are poles and so forth, you don't care, just take log. But the constant determined by the local situation. So locally, they don't have poles. For every point in the neighborhood, you can do it. But then you put this thing globally, you get this result. And then there is the logarithmic derivative lemma. So the log plus of the pullback of the differential of the log is of the log order of the characteristic function. Okay. So this is a bit technical. Outside a certain set whose measure can be controlled. And TRF is never-linear characteristic function. And the reason why the log of global meromorphic functions use a local coordinate is in order to apply this. Right. And then, of course, this part here, using the log of global meromorphic functions as local coordinates would give you this, because you estimate by the logarithmic lemma, you get this. And so the pullback, of course, is the holomorphic function. And then you have this the usual definition of the characteristic function of the pullback is estimated by log plus. And then on the other hand, because the holomorphic jet differential vanishes on D, that means that this characteristic here dominates the counting function. And then the amplitude of D means that the counting function dominates some positive constant times the characteristic function. And therefore, finally, you use the contradiction here, that the characteristic is dominated by the log order. And so that is how it's proved. And this is a very ingenious argument, actually. It also tells you that the Schwarz lemma, the main point is the logarithmic derivative lemma. And in Bloch's paper, he commented that if the logarithmic lemma holds, then it works. But he was not aware that already was proved by the limit. And another thing is how to produce this holomorphic jet differential so that you can pull back. So we digress here to make some comments related to the Schwarz lemma for entire curves. So when there are sufficiently independent holomorphic K-jet differentials of weight M on a complex manifold vanishing on some ample divisor without common base point sets. Okay. So each one, of course, has vanished on an ample divisor. But you may be able to find enough of them so that they don't have any base point sets. Okay. And if that's such a case, then you can take the sum of squares. And then it defines a smooth jet metric. Okay. So it's not the usual metric because it's, you need the jet to evaluate it. So it's known as the jet metric. And the jet metric has curvature, and the curvature is strictly negative. Okay. So the argument of Schwarz lemma for entire curves work for the more general case of a smooth jet metric with strictly negative curvature instead of a single holomorphic jet differential vanishing on an ample divisor. Because in the argument given, it works only with logarithmic derivative lemma using log of global Merinoid function in local coordinates. But if you have a jet metric, actually the argument could be extended to handle the jet metric. So the Pobel jet metric should be 0. Using the same technique. The same technique is the log of global Merinoid function should be used in local coordinates. So if there is a smooth jet metric with strictly negative curvature on some special complex hypersurface, it can be extended to smooth jet metrics with strictly negative curvature on neighboring complex hypersurfaces. That's the key point. So if you have some complex hypersurface and you have holomorphic jet differential, you cannot just move it next door a little bit. Okay. But once you know that the jet metric is smooth, you can always extend a smooth function a little bit in the neighborhood. Yeah. And then in that case, a good choice of some special hypersurface enables us to construct such a jet metric so that we can reduce the lower bound of the degree of generic hypersurface degree n to guarantee hyperbolicity. Reduce the lower bound to polynomial order. And once you have a good smooth metric on neighboring hypersurfaces, we can use the metric to construct holomorphic K-jet differential of weight nm for n sufficiently large, because you may have to raise to higher power in order to construct it. So therefore, on the universal hypersurface, outside a proper subvariety of parameter space of coefficients, there are sufficiently independent holomorphic families of holomorphic K-jet differential of weight nm vanishing on an ample. And this part is very important. The idea of using a jet metric with strictly negative curvature in the case of Riemann surface is already done in a paper by Grauer and his daughter Peter Nell. An entire curve is a holomorphic image of a compact Riemann surface of genus 0 with one puncture. And by requiring sufficient ampleness of divisor where a holomorphic K-jet differential vanishes, the Schwarz lemma also holds for compact Riemann surface general genus with general number of punctures. because what for the entire curve, the trouble is with what happens to the puncture. It's the essential singularity. But if you have a higher genus and many more punctures, the corresponding thing works with more condition on the vanishing of the holomorphic jet differential. So with the use of jet metric with negative curvature, the ampleness of cotangent bundle is replaced by the ampleness of the bundle of jet differentials. So here we could construct things only when you look at jet differentials. But of course, one of the themes of the conference is about the cotangent bundle, the ampleness. Okay, so I just want to point out the connection. So this kind of technique handles the ampleness of bundle of jet differentials instead of cotangent bundle, because the cotangent bundle would be the bundle of one jet differentials. Now, this is the end of our digression related to the Schwarz lemma, and now we turn to Bloch's method. So, Bloch's method, after getting the Schwarz lemma, the second step is how to construct holomorphic jet differentials, because you have to get them. And he introduced an important idea, which I call position for getting map in abelian variety setting. So when you have a compact complex manifold, define the space of all k jets, or jkx. And a k jet at one point is given by a local holomorphic function from an open unit disk D with coordinate zeta to x, so that the origin is mapped to the point, but you only take the part up to order k, so module zeta to power k plus 1. So the k jet part. And so k equal to 1, of course, is J1x is just a tangent space, because it's just a tangent to a curve. For abelian variety of complex dimension n, jk of A would be A itself times the part obtained by a differential of the coordinates. Okay, and there are n coordinates, and each one differentiated up to n k times. So this is the same as the jk. And now there's a position for getting mapped, and it's a mapping the jet space to the jets, and forget about the positions. So it's a map onto the second factor, and that is the position for getting mapped. And how is this to be used? Now, you take a non-constant entire curves in an n-dimensional abelian variety. So we can look at the image of the kth differential of the map. Okay. And you take the Zariski closure. So the Zariski closure will be in jk of A. So in particular, when k is 0, it's just the Zariski closure of the image of C. And now you look at the position for getting map, restricted to the closure of the kth differential of the defining map for the curve. Then you assume that this one here, the image, and the Zariski closure, and the Zariski closure has dimension m, which is less than n. Okay. Then here is Bloch's idea of using the position for getting map. He said that if you look at this position for getting map, okay, and if the fibers are not generically finite, okay, so you have a lot of fibers, and if everyone is not finite, then it's not generically finite. The translate of A by some so if the fibers are not generically finite, then there is some non-zero vector in A whose translation maps x to x. So if you have the case of generically non-finite fiber, then you have a direction which translates the subspace X to itself. That is the important thing. And how is this done? So because this is an important step, this is done in the following way. You just trace the definition. So you have local coordinates for X, which is the closure, Zariski closure of the image. And then you look at a generic point. And then locally, the tangent space will be defined by one form. Actually, there are n minus m one form because it's dimension m. Okay. And so the tangent space is defined by its vanishing. And suppose you don't have the finite fiber condition. It means that at every point, generically, there were directions in the fiber that is mapped to a point. Okay. So there would be a constant depending on that point, giving you the non-zero tangent. And then the map actually is defined at the jet level. Okay. So that means that if you differentiate up to order m, you still have this condition. So you end up with something like this. And then by the Wronskian argument applied to these functions, you conclude that the C's are constant. So that's the key point that he used, the position forgetting map. And then you get a non-zero vector because now it's independent of the point, and translation would map X to itself. Okay. So how do you use this to construct jet differentials? And it's done by the extension field property of the Meromori function field defined by the position forgetting map. You see, you have a map of generic finite fiber, then the Meromori function field would be a finite extension. Okay. And then you can use it to construct it. So here, you reduce the subvariety of K-jet space of an n-dimensional abelian variety A, such that the map induced by the position forgetting operation has generic finite fiber. Then what happens is that you take an ample divisor on a abelian variety and look at its inverse image. So here, this map is the other map. This map just picks out the direction. This is position. This is the position forgetting map. This map picks up the position. And you have an ample divisor D, and you can take this inverse, and then you look at the Meromori function field. And in the Meromori function, there exists a polynomial in this part here, so that when you pull back, it vanishes on this, because this is a finite fiber thing, and the Meromori function field is finite extension. So there exists a polynomial here, which vanishes on the inverse of the ample divisor. And then you would be able to get the polynomial here. You know, one of the coefficients would serve the purpose. So the jet differential actually is obtained as a polynomial in a differential of the coordinates of abelian variety with constant coefficients. There exists one of them that works. Okay. So this is an important technique. So let us look at it more closely. So you take a Meromori function on A, whose whole set is a positive multiple of D. Then the generic finite fiber condition implies that the pullback from the position picking map belongs to a finite extension of the field of all rational functions on C and K. And then there exist polynomials with constant coefficients in the differential of the variables, such that it satisfies the equation, because this equation defines the finite field extension. So this element here belongs to the finite field extensions. It satisfies the polynomials with coefficients here. And then you look at the top degree one, is not identical to 0. And then you can set P to be that, so that it vanishes on the divisor there. So this is the important technique of handling it. It's amazing that all these things come together. So if you look back at Bloch's theorem, it tells you a abelian variety, and phi is a nonconstant holomorphic map. And if you take the Zariski closure of the image of the map, then X itself must be the translate of some abelian variety. And now it comes together from the above techniques. So assume that if X is not a translate of abelian subvariety, then you can take the quotient of A by the subgroup elements, which translates, leave X invariant. And then you take the quotient. So, and then look at the quotient situation. In the quotient situation, then the subvariety is not invariant by any translate, because you have quotient out all the translates involved. So Bloch's theorem follows from the above three techniques. So generic finite fiber, construction of holomorphic jet differential vanishing, and then so on and so on. Okay. So the reason why I spend time doing this is that I believe that this is the technique that is important not for abelian variety, but for the general case. Because there are a lot of really ingenious techniques involved. Okay. So let me say something about a number theory analog of Bloch's theorem. So if A is a abelian variety, defined over a number field K. So assume that X is a subvariety, so that X does not contain any translate of a positive dimensional abelian subvariety. So it's the same setup as in the function theory case, except that things are defined over a number field. The conclusion is that X contains only finitely many K rational points. Yeah. And so this you can find in Farthing's paper, which is a generalization of his result on Model conjecture about the number of K rational points in a compact Riemann circle genus bigger than 1 over a number field. But the proof is based on the idea of Voiter, so I attribute it to Voiter Farthings. Okay. So what is the difference between these Voiter Farthing techniques and Bloch's? Okay. The difference is that the role of a differential operator in the use of holomorphic jet differential in function theory is now replaced by the role of the difference operator, not the differentiation operator, difference operator in number theory. And the properties of the addition operator for abelian variety, especially in terms of heights of K rational points, are important ingredients in the number theory setting. Yeah. Now, of course, I don't plan to go into the details, but I just want to give two examples of parallelism between techniques used in function theory setting and the number theory setting, to give you some idea of how the things are related. So the first thing is about the generic finite fiber analog. So because remember that the generic finite fiber condition is important because it gives you the finite extension of the monomorphic function field, and from which you can produce holomorphic jet differentials, which are polynomials of the differential of the coordinates with constant coefficients. Yeah? And so in that case, here is the analog. The analog is, in the case of number theory, instead of the position forgetting map, here is the map here. The map maps to the difference. the position for getting maps to the differentials, remember. Okay. But here it is being mapped to the difference. And of course, you know, what is the jet space? The jet space is replaced by the product of the manifold. Okay. So this is plotted out by Voiter. And the jet space of order m-1 in Bloch's function theory case is replaced by a product of m copies of x, because the differential is replaced by the difference. Okay. So plus the original one. So if you have the jet space of order m-1 would be a product of m. So product of m of them. So this is the jet space m-1. And then here would be the differentials. So that is Voiter's formulation, and say that this is generically finite onto its image here. So it's the analog of that particular step. And then another one I want to point out is the situation of vanishing on an M-pole divisor, because holomorphic jet differential vanishing on an M-pole divisor. And so if you look at the case of a beam variety over a number K, first one looked at a very ample symmetric line bundle, so that you can use it to embed the beam variety. Okay. Symmetric means that's invariant under the map from x going to minus x. So now you let x be an irreducible subvariety which does not contain any translatable beam variety of x. Yeah. So for rational positive numbers here, we define the Q line bundle like this. So it's a pullback of the projection, and then the pullback of the difference. But the difference with some coefficients here. And this is on A to a certain power, which is the same as the jet differential, actually. Jet differential m-1. And so the projection P out I is projection of I factor. And the statement is that there exists an epsilon 0, so that for any epsilon less than epsilon 0, there exists a real number s. So that if the choice here, the successive quotient at least x, then this one is ample on x raised to the power m, which actually means, so let's go back, which is actually means that we are located at the analog or holomorphic jet differentials vanished on an ample divisor. Okay. The ample divisor used is given by this epsilon. So this epsilon here, that is the vanishing order. Okay. So that was actually used by Faltings. Yeah. So we just point out the examples. So now let's look at the case of hypersurface. What happens? Because you want to do hypersurface number theory, but at this point there are still problems. So let's look at the construction of jet differential hypersurface at high degree. Okay. And the construction up to this point involves counting vanishing in pole order. So let me explain. It's a very straightforward thing. You take a plane curve defined by FZW equal to 0 degree at least 3 in affine coordinates of P2. So a plane curve. Okay. So a plane curve, you can get a holomorphic one form. Is usually constructed like this: a dw divided by f sub c, which is derivative of f. Okay. And you look at it. What does it mean? It means that you take dw, which is a meromorphic one form, because w is the affine coordinate, is a pole. Okay. But if you reshape the meromorphic one form to the curve c, then that means that you have this situation: f equal to df equal to 0. Then this meromorphic one form gets some vanishing order from these equations. And the vanishing orders can be offset by dividing by this. Okay. So it's just precisely the vanishing order coming from this. After you recheck it, that's it. And you can do this for any hypersurface. Okay. So similarly, you take the following thing. Instead of dw, you take a meromorphic n-jet differential as a polynomial here, okay, of the differentials of affine coordinates with constant coefficients. So it's the same as this dw, which is only 1. Okay. And here you take, instead of 1, you take the differentials and take a polynomial with constant coefficients. Okay. And then you restrict to a complex hypersurface of sufficiently high degree and defined by a function. And then when you restrict, of course, then you have f, df, dn, f equal to 0. You look at n-jet, precisely the same as before. Of course, the n is no longer 1. And then you divide it by the vanishing order coming from these. And you divide by fz1 minus 1. And then you say, why divide by fz1 minus 1 instead of fz1? It is actually the same. The difference is that if you use fz1 minus 1 as the fz1, then when you do the computation, if you restrict to fz1 equal to 1, then the coefficient of dc1 equal to 1, making it easier to compute. So it's just a technical point. Okay. So you see that this is completely analogous to the case of the curve. Okay. No big deal. Okay. So then you count the same as before. You count the vanishing order and the pole order. That's it. So you have the homogeneous weight of these. You call this m, and then you now allow this Q to have coefficients which are polynomials in C1, Cn plus 1. Okay. So there's a difference. The difference in dimension 1 case is that you only have this part here, and the coefficients are just 1. And here, the coefficient with polynomial of a certain degree. And then the degree of the hypersurface has to dominate this. So in that case, the Q cannot be identically 0. So here's the typo. This is the n instead of n minus 1. The space of n jets of the hypersurface degree delta for any choice. So you consider these polynomials with constant coefficient in these and in these various degrees. Then you restrict it, and then they are non-zero. So you can count the number of possibilities by looking at number of coefficients and count the number needed for the jet differential to vanish on this. Just compare, just count it. And then you end up with the condition. So here's the exact statement. So with these numbers, so they exist an explicit number from the counting, so that they exist a holomorphic n-jet differential not identically 0 with vanishing order Q. And as long as Q satisfies all these conditions. So it's something explicit, and you say it looks complicated. Indeed, it looks complicated because the counting involves binomial coefficients. You just count the number of possibilities of a polynomial degree. And then that's the reason why it involves exponential expressions like this. Okay. That is unsatisfactory part. And then after you do this counting, you can only get a single one. But we need to get more so that we can take the sum of the absolute value and so forth, right? And here you don't. So there's another technique. And the technique is called slanted vector fields on universal hypersurface. So the condition holds only for generic hypersurface. So to use a generic condition, we need the universal complex hypersurface. That means that here you use the space of all coefficients of the equation defining the hypersurface. And so this is a universal hypersurface. And then here's the technique. You look at EP, which is the n plus 1 tuple, whose non-zero entry is 1. And then you take two indices so that they differ only in one of them. And you can look at this vector field. This vector field involves differentiation of the coefficients. And it has pole order because it involves the affine coordinate. But it has vertical pole order only, pole order 1. Okay. The reason why this works is that when you look at the universal hypersurface, look at the equation and regard the coefficients as variables, then the coefficient occur only in degree 1. That's the reason why you get this situation. Then you can actually get meromorphic vector fields, which has very low vertical pole order 1. Okay, that's important. And then, so these are what I call slanter vector fields, because they have non-trivial contribution from the coefficient of defining equation. And this method enables us to construct explicit slanted mirror vector fields on the vertical n-jet space. So here, this one is only on the tangent space. Okay, this one on the tangent space. But we need a jet space. So we can do similar things for the jet space. And we look at the jet space only along the vertical direction. And then the vertical pole order is not just 1, but it's of this order. And it can be improved also. But this is a square order for the jet differentials, because you are summing up essentially 1, 2, and so forth. So the vertical jet space, only jets in the vertical directions are considered, which means that when you differentiate f, the coefficients are regarded as constant. Okay. And slanted means not vertical, that means non-trivial contribution from the coefficients of f. Okay. So the use of slanter vector fields of low vertical order is motivated by the work of Clemens, I, and Vassin. And this is considered as a function theoretical analog of that, of these 3 papers. And then when you use the meromorphic slanted vector fields of low pole order and apply it to a holomorphic jet differential vanishing to high pole order, then you end up with new ones. Okay, that's the standard technique of using the slanter vector fields. You apply the lead derivative action of slanted meromorphic vector fields, and then you come to a holomorphic jet differential constructed above by counting the vanishing and pole orders. Okay. And then the construction would give you enough to eliminate the base concept. Okay. So now, let me tell you the new method, okay, because we don't want this exponential dependence. Yeah. So what is the new method? The new method to eliminate the base concept is to imitate Bloch's idea. So the Bloch's idea applied to the hypersurface case would help us reduce the generic hypersurface degree to much lower than the exponential one. And we can only reduce it to polynomial order. It's very difficult to get down to linear order. Okay. So we are going to imitate Bloch's. Okay. And the hope is that it could be translated to the number theory case, but as I said, that there are still difficulties there. Okay. So at that Bloch's method of position for getting map, now you need some modifications. Okay. So what are the modifications? First of all, the modifications, the first one is that when you take a position for getting map, you need some global coordinates for the tangent space before you can forget about the positions. Okay. So in this case, you don't have it. For projective space, you don't have the global one. So what do you do? So in this case, we only focus on the affine part. But when you focus on the affine part, there will be poles at the infinity part. In the second place, in Bloch's case, the ambient space of invariety, so it's completely flat. In the case of projective space, it's not flat. So in the case of Bloch, you can construct the holomorphic jet differentials by taking polynomials in the differentials of coordinates with constant coefficients, because it's flat. But in this case, it's not flat because the projective space has some curvature. So the coefficients need to depend on the coordinates, affine coordinates, the polynomial low degree, to offset curvature, you need to have the coefficients as polynomials in the affine coordinates. Okay. So, but then how do you do the construction? The ideal construction is that you can do this for some special ones, and then by using the technique of slanted Marmol jet differentials to move to neighboring ones. Okay, so that's the idea. So what is the easiest one? Is a Fermat hypersurface, the simplest one. So let's just look at the hypersurface of Fermat, like this. Okay. Now in this case, what happens is that we have again the position forgetting mapping. Okay. And then the jet space and so forth, because now complete is the affine case. Okay. So in that case, what you do is you differentiate the defining function n times. Yeah. So the same thing. It's very easy to see. So here would be the functions. Okay. All you have to do is just differentiate. You get this. Okay. When you get this, the coefficients, which depends on delta, gets the exponent reduced by 1 in each step. In each step is reduced by 1, of course, when you differentiate. Yeah. And then something else. Okay. And now you can look at the equation and try to solve for these, because z to a certain power appears in everyone. The first one is degree delta. When you go down, it's delta minus 1 and so forth. The worst is delta minus n. But at least everyone has the unknown Cj delta minus n. And you can solve for it by Cramer's rule. So here is the coefficient matrix, the Cramer's rule. So for everyone, you have a power here. And then the right-hand side would be just the column vector with only one entry minus 1. And then, of course, now the Cramer's rule would give you this solution of the unknown. So here's the main point. Then this part here is divisible by this. On the other hand, we know what this thing is. This thing is explicitly given by all the g's and so forth. Okay. We're given by all these g's here. All these g's. And the g's would have very bounded pole order. So then we end up with the fact that we get these things of bounded pole order and yet vanishing to high order. So that means they define a holomorphic jet differential vanishing to a high order depending on how high delta is. Okay. So this is a very special case. And of course, for the special case, we end up with delta like bigger than or equal to n square. But then it's useless because we have to be able to get enough of them to eliminate the base one set. And we cannot eliminate here, in this case, as a matter of fact, for Fermat surface, Fermat hypersurface, we always have special entire curves inside. So we know that we cannot get enough to eliminate the base one set. So to eliminate the base one set, we need to use the coefficients and the slanted differentials. Okay. But we don't need to use all the coefficients. We don't enough coefficients to get the slanted Marmol function field, Marmol vector field work. That's enough. So the idea is to modify the Fermat hypersurface by adding some coefficients. So here is a modification for the Fermat hypersurface. So you take a polynomial of low degree eta, and then instead of the Fermat hypersurface, we add the coefficients here of low degree. So there's some coefficients enter, enough coefficients enter. And we can just repeat the same construction. Here you have the same thing, and then you have the coefficient matrix, and then you have the Cramer's rule. You do the same thing. And then here, you can count the pole order and then you encounter vanishing order here to make up for it. So then you end up with the statement that you do get some holomorphic jet differential vanishing on M pole here. But that eta enters. But then you have now some coefficients to help you. And then you use those coefficients to help you get the slanted meromorphic function, a meromorphic vector field. And you need enough of them. And what do you mean enough of them? So first you use a part of the coefficients, and then you get the slanted meromorphic vector field to cut down on the base one set. And then add some more, okay, a little bit more, so that the other one is transversely cut down still, but you cut down the next one and so forth. And then you eventually eliminate it completely. And of course, this one here, this technique would give you only polynomial order in the degree of the hypersurface. You don't get to the linear order. Okay? The linear order is very hard, of course. It's like the linear order in Fujita conjecture. It may be possible to cut it down to order n squared because you eliminate one thing at a time, one dimension at a time, just like the Fujita conjecture. But the linear order is different. So finally, I want to point out one thing. Because the tool used is a slanted meromorphic vector field. Okay. So it's the technique of Clemens, Einstein, and so forth. But you can also look at it from the point of view of slanting a hypersurface. So here is how it works. So you take a finite subset, and then you look at polynomials whose degree are low, and then what you do is that you replace some of the terms by polynomials here. So in that case, if you replace the coefficients of the defining equation by polynomials, then you get a slanted hypersurface. And the limiting case actually is the slanted meromorphic vector field. So you get a hypersurface, and then you have some coefficients. And you can choose some of the coefficients, replace the coefficients by a polynomial low degree in the variables. So your hypersurface is slanted, so to speak, in the universal hypersurface. And then the limiting situation is actually the slanted vector field. So that's another way of looking at it. Yeah. Okay, I think I'll stop here. And, thank you.
Are there any questions? This is also for the audience on Zoom.
So raising the degree means making the canonical bundle more and more ample.
That's right, yeah. So
Another way to do that is to take branch coverings of higher and higher degree. And I seem to remember an old result along the lines that generically, if you take a branch covering of something with positive canonical bundle, take sufficient time, then you get generically again the same result.